Dear students, welcome you all for our lecture series on agrochemicals and pesticides. In today's episode, we are going to discuss about the topic analytical techniques involved in pesticide analysis. Let us see introduction. Pesticides are widely used to control household, agriculture and forestry pests. The application of pesticides for controlling pests has recently shown a tendency towards combination of two or more pesticides for diverse reasons, such as for increasing their effectiveness, for controlling more than one pest at a time, and for increasing the storage life of insecticides. The interest in the development of good methods for the simultaneous determination of pesticides has increased greatly in recent years. Because of the heavy use of pesticides in agriculture and their presence in the environment and foodstuffs. Gas chromatography with selective detectors such as electron ionization mass spectrometer and electron capture provide sensitive methods for measuring pesticides. Hence, in this episode, the following aspects are going to be seen. Methods used for the analysis of pesticides, HPLC methods for pesticide analysis, volatile organic compounds, instrumental analytical methods and non-instrumental technique. Let us see the first aspect, methods used for the analysis of pesticides. Pesticides have become the part and parcel of modern day agriculture. Pesticides are not only an agricultural commodity, but find use in non-agricultural regions. But the very nature of the pesticides to kill renders them harmful for the humans and other living beings. Their extensive use has contaminated our soil, water and food, thus risking our well-being. Many persistent pesticides and their degradation products penetrate into the plant tissues or stay in the water and soil, thus appearing in our food chain. The pesticide residues are magnified during food processing, thus making even the processed foods storage house of harmful chemicals. Taking into account the rampant use of pesticides which has led to the contamination of various strata, continuous monitoring of environmental and food samples is of utmost importance. Over the years, pesticides have been determined by many conventional as well as modern day methods like spectrophotometry, polarography, thin layer chromatography TLC, Fourier transform infrared FTIR, high performance liquid chromatography HPLC methods using different detectors, gas chromatographic technique using various detectors or in combination with mass spectrometry, capillary electrophoresis, micellar electrokinetic chromatography. Extensive research has been carried out on the analysis of pesticide residues in foodstuffs and environmental matrices. The effect of pesticide exposure on the agricultural workers and children has also been the topic of research for many scientists. Let us see some methods. Thin layer chromatography TLC is a chromatographic technique used to separate the components of a mixture using a thin stationary phase supported by an inert backing. The separation depends on the relative affinity of compounds towards stationary and mobile phase. The compounds under the influence of mobile phase travel over the surface of stationary phase. During this movement, the compounds with higher affinity to stationary phase travel slowly, while the others travel faster. Thus, separation of components in the mixture is achieved. Once separation occurs, individual components are visualized as parts at respective level of travel on the plate. Their nature or character are identified by means of suitable detection techniques. Thin layer chromatography system components. Thin layer chromatography system consists of thin layer chromatography plates, preferably ready-made with stationary phase. These are stable and chemically inert plates onto whose surface a thin layer of stationary phase is applied. The stationary phase on the plates is of uniform thickness and consists of fine particle size. Thin layer chromatography chamber. This is used for the development of thin layer chromatography plate. The chamber maintains uniform environment inside for proper development of spots. It also prevents the evaporation of solvents and keep the process dust free. Mobile phase. This comprises of a solvent or solvent mixture recommended for the purpose. The mobile phase used should be particulate free and of highest purity for proper development of thin layer chromatography spots. The solvents recommended are chemically inert with the sample stationary phase. A filter paper moistened in the mobile phase to be placed inside the chamber. This helps uniform rise in mobile phase over the length stationary phase. Column chromatography. Column chromatography is the actual or the basic type of chromatography procedure which was developed during early stages of chromatography discovery. From it, the principle of chromatography is described and these are still followed in the most advanced modes of chromatography. Other types of chromatography methods were developed with column chromatography as a module and with slight variations. Column chromatography is basically a type of adsorption chromatography techniques. Here, the separation of components depends upon the extent of adsorption to stationary phase. Here, the stationary phase is a solid material packed in a vertical column made of glass or metal. Principle: when a mixture of mobile phase and sample to be separated are introduced from top of the column, the individual components of mixture move with different rates. Those with lower affinity and adsorption to stationary phase move faster and eluted out first, while those with greater adsorption affinity move or travel slower and eluted out last. The solute molecules adsorb to the column in a reversible manner. The rate of the movement of the components is given as follows: R is equal to rate of movement of a component by rate of movement of mobile phase. That is, it is the ratio of distance moved by solute to the distance moved by solvent. Requirements: the column chromatography requires a vertical column with a knob at the bottom end. This is preferably a burette shaped cylindrical column without graduations or readings. Stationary phase or adsorbent, mostly fine sand will do, are that recommended for the experiment. The particles of stationary phase should be of uniform size and shape without contamination. Mobile phase, preferably solvents of chromatography grade, either a single solvent or a mixture of solvents as required for the separation. Cotton wool or asbestos pad to plug the exit of column at the bottom and thereby hold the column of stationary phase and let only escape of solvent and sample. Procedure: the stationary phase material is suitably moistened with mobile phase and packed sufficiently in the column with a cotton or asbestos pad at the bottom. The extract material or sample to be separated is placed on the top of the packed stationary phase. The mobile phase is poured into the column over the sample. A collecting beaker is placed at the bottom of the column near the end to collect the elute. Precautions: keep the column in a clean and dust-free place. Do not disturb the column till the separation is complete. Avoid gaps within the stationary phase packing. Applications: column chromatography is best suited to separate active principle from plant materials. In separation of compounds after organic synthesis to obtain desired molecule. To separate or purify natural compound mixtures like alkaloids and glycosides. Let us come to the second aspect, high performance liquid chromatography, that is HPLC method for pesticide analysis. Chromatographic analysis is the most sought after technique for pesticide residue analysis, whether gas chromatography, liquid chromatography, or in combination with liquid chromatography and applying from the wide range of detectors available like ultraviolet chemiluminescence, electrochemical detector, nitrogen phosphorus detector, fluorescence detector, etc. High performance liquid chromatography is a creditable method for the analysis of wide variety of pesticides. Several heat unstable and polar pesticides show better detection with this technique. Analytical order of chemicals in the environmental samples. In order to be able to determine very small amounts of chemicals in the environment, it is necessary to follow a series of operations. The first one, isolation, that is extraction and separation of the target chemicals from sample matrix, that is air, water, sediment, living things, etc. Second one, separation and purification of the target chemical from co-extracted non-target chemicals, that is sample cleanup. The next one, sample concentration. And the fourth one, measurement by highly selective and sensitive analytical equipment such as gas chromatography, mass spectrometry. Occasionally, it is also necessary to chemically modify non-volatile and heat degradable target chemicals prior to analysis by the two most commonly used instrumental methods in environmental analysis, gas chromatography or gas chromatography mass spectrometry. The following sections describe this series of analytical operations in more detail and introduce of the main analytical methods for environmental pollutants. Let us come to the third aspect, volatile organic compounds. The two main methods for the isolation of volatile organic compounds from water are the per gun trap method and headspace method. Per gun trap method. This method, also known as the dynamic headspace method, removes volatile compounds from the sample matrix by passing an inert gas such as helium or nitrogen through the matrix. The target volatile compounds are desorbed from the aqueous phase to the gas phase and are then separated from the stream of gas by adsorbent filters. The adsorbent material is then heated in a stream of gas chromatography carrier gas. This releases the trapped substances into the carrier gas. The target analytes are introduced to gas chromatography and analyzed. Typical trapping materials are porous polymer beads, activated charcoal, silica gel, other gas chromatography column packing materials or combinations of such materials. Practically, this method can only be undertaken using one of a few specified instruments which are fully automated from the purging step through trapping, releasing the target analytes and introduction into the gas chromatography. Headspace method, also known as the static headspace method. This method is less sensitive compared to the per gun trap method, but operation is simple, easily automated. The sample is placed in a sealed container such as a vial and left at a constant temperature until the gas and liquid phase are in equilibrium. The target substances in the gas phase are collected by gas tight syringe. This is injected into the gas chromatography mass spectrometry. Calibration curve are made by dissolving the target chemicals in purified water and then treated in the same manner. However, the air liquid phase equilibrium is very much affected by matrix in which the sample is dissolved. So, in a lot of cases, standards dissolved in purified water might not be appropriate surrogates from which to prepare calibration curves. In such cases, it is necessary to saturate samples with salt, add an external standard and then quantify the target chemicals. Also, for samples which exist as ions in water, the pH must be adjusted. For example, it is easy to analyze fatty acids in alkaline solution if first the solution containing the fatty acids is acidified by sulfuric acid. It should be noted that pH adjustment is also often needed for the Pergun trap method. Let us see the fourth aspect, instrumental analytical methods. Only gas chromatography mass spectrometry is discussed hereafter because of the eye sensitivity, eye selectivity, universality and the large amount of information available on what is often considered the most appropriate analytical instrument for environmental analysis. Gas chromatography mass spectrometry analysis, it is not too much to say that whether trace chemical analysis by gas chromatography mass spectrometry is successful or not depends on whether the setup of the gas chromatography is appropriate for the target compounds or not. However, in order to analyze chemicals at sub-nanogram concentrations efficiently and accurately, it is still necessary to carefully choose columns, sample injection conditions, column temperature conditions, etc. Selection of quantifying ions directly affects mass spectrometry identification and detection limit. Here follows some basic information which should be known when trace chemicals are to be identified and quantified by capillary gas chromatography mass spectrometry and things which should be considered when undertaking gas chromatography mass spectrometry. Mass spectrometry. There are two ways to use mass spectrometers in scanning mode or selected ion monitoring mode, that is SIM. In order to select the appropriate operating mode, one must understand some of the key features of these methods. Scanning method. When operated in the scanning mode, the mass spectrometer records the mass spectrum of all ions detected within a defined mass range by scanning at predetermined mass intervals. The record of total ion intensity on each scan with time is called the total ion chromatogram, that is TIC. The total ion chromatogram is equivalent to, for instance, a gas chromatography flame ionization detector GCFID chromatogram. The data making up the total ion chromatogram is recorded electronically and specific predetermined mass intervals information can be extracted and printed. These latter are called mass chromatograms. The scanning method can change identifying ion freely after analysis and there is often no need to reanalyze the sample even if there are interfering peaks. The accuracy and reliability of analyte identification is significantly better than selected ion monitoring mode because one can obtain the mass spectrum of the target compound using the scanning method. However, the method's sensitivity is theoretically much worse than selected ion monitoring mode in the case of magnetic field type quadrupole mass spectrometers. Low resolution mass spectrometry cannot perform trace analysis. Finally, the amount of data collected is extremely large compared to selected ion monitoring mode. Let us come to the fifth and last aspect of this topic, non-instrumental technique. Titration is a common method for determining the amount or concentration of an unknown substance. The method is easy to use if the quantitative relationship between two reacting substances is known. The method is particularly well suited to acid-base and oxidation reduction reactions. Acid-base titrations are usually used to find the amount of a known acidic or basic substance through acid-base reactions. The analyte is the solution with an unknown molarity. The reagent is the solution with a known molarity that will react with the analyte. A redox titration is a type of titration based on a redox reaction between the analyte and titrant. Redox titration may involve the use of a redox indicator and or a potentiometer. A common example of a redox titration is treating a solution of iodine with a reducing agent and using starch as an indicator. A reaction in which the analyte and titrant form an insoluble precipitate also can serve as the basis for a titration. We call this type of titration a precipitation titration. Complexometric titration, sometimes chelatometry, is a form of volumetric analysis in which the formation of a colored complex is used to indicate the end point of a titration. Complexometric titrations are particularly useful for the determination of a mixture of different metal ions in solution. Gravimetric analysis or gravimetric determination is a method of quantitative analysis in analytical chemistry in which any element or compound gets precipitated from its solution by using suitable reagent. Let us come to the conclusion. The large number of potentially hazardous analytes in environmental samples coupled with deficiencies in currently available organic analytical techniques make routine environmental analysis of gas chromatographicable volatiles extremely difficult. This is all about the topic analytical techniques involved in pesticide analysis. So, students, hope you enjoyed this session. We will meet in the next episode. Thank you.